So, from chapter 14, before we move on, first issue is the term at least. And even though I did a bunch of examples, like on your homework, and we talked about it yesterday, where people are still missing at least. All right. So we talked about this, like these screenshots are from chapter 4 or chapter 14. Like we already looked at these more, but again, I've got more examples and stuff. So the phrase at least should make you think about the complement. So for example, on the practice quiz, one of the questions, there's 5 multiple choice questions, right, with 4 choices each. And one said, like, what's the probability of getting at least 1 correct? Right? Was it wrong? Okay, on the quiz, at least 1 incorrect. Alright, so if it says at least 1 incorrect, if you were trying to find all of those probabilities, that would mean, like, at least 1 incorrect would mean 1 incorrect and 4 correct, or 2 incorrect and 3 correct, and so on and so forth. That's a lot of work. So you could also do whatever's left over. So at least 1 on that question would be 1 question incorrect, 2 questions incorrect, 3 questions incorrect, 4 questions incorrect, 5 questions incorrect. But the other choice still available is 0 questions incorrect, right? So at least it's going to be whatever, hopefully you're going to do 1 minus whatever it is not. So we've done a few of these, and we keep doing them, but I'm going to keep doing more of them, so that hopefully we get better at it. Yes. So I've got some examples. We're not going to do all of the individual pieces here. We're going to focus on maybe 1 or 2, and then do one of the at least ones. And if you don't mind, I'm not going to actually calculate them. I've already calculated them, but we'll set it all up together, and I'll show you what the answer would be. All right. So, dice. You roll a fair die 3 times. Make sure you're reading how many times things are happening. What is the probability of that? So let's start with an easy one, and then we'll get into at least. These are all in your book on page 340. These are ones I didn't assign for homework. They're just extras. So what's the probability that you roll all 6s? So how would we set that one up? 1 over 6. What about 1 over 6? To the 3rd power, right? 3 separate rolls. Does 1 roll influence the roll before it? No, so they're all independent. So we can just multiply them. That ends up being, if you're interested, approximately 0.0046. Okay. We can do those, right? You guys can do those. You did great on the quiz until I got to the at least question. So let's talk about D. You roll at least 1 5. So that would be re-rolling 1 5 or 2 5s or 3 5s, or you just 1 minus no 5s, right? Does that make sense? So 1 minus the probability of getting no 5s. So how do I find the probability of getting no 5s? 5 over 6 to the 3rd. So this ends up being 1 minus 0.578. It's approximately 114. What about E? It says the numbers you roll are not all 5s. How can I reword that to sound like it to be an at least question? So that's really what it is in its essence. The numbers you roll are not all 5s. Right, so at least 1 is not a 5. So using this idea of the complement with these at least questions, how are you going to figure out at least 1 is not a 5? 1 minus probably all our 5s. So this is almost the same, right? A little bit different. So what's probably getting a 5? 1/6 to the 3rd. ends up being 0.995. Is at least making more sense. I'm just going to do more examples. I don't know how else to make it make sense, just to do more examples. If that works for you, that's good. Way to think about it. That's good. Okay. Do you want to do a question about bowlers or voters? Bowlers. Okay. A certain bowler can bowl a strike 70% of the time. So what's the probability that let's do B first, makes her first strike in the third frame? What does that mean? Right, so she doesn't make a strike the first frame. So what's the probability of not making a strike? And then, yeah, she doesn't make a strike again. And then she makes a strike. Right? Again. In notation. So you have the probability of, you can write strike 1 on the third frame. And then if you were trying to use set notation, you'd have the probability of not a strike and not a strike and strike. You can write the word and. You can write the word and instead of using set notation. On your quiz, all I really wanted you guys to see was have some sort of notation and then to show your work in some way. So you don't have, I mean, you could have, Jacob, you could have written this, and then that, and then your answer. And that would be acceptable. I'm trying to get you guys in the habit of writing the notation and writing some work down so that on the AP exam, on the free response question, you just don't write a number. Right? Okay. On part C, well, I guess I could give you the answer. Half of you guys already figured it out. Yeah, so what's the probability that you have at least one strike in the first 3 frames? 1 minus what? Probability of no strikes. And we're only talking about the first 3 frames, right? So number-wise, what would this look like? 0.3 to the third. Excellent. See, you guys do these now. Why couldn't you do them yesterday? A lot, this is like honestly on the quiz yesterday, a lot of them I got, it said at least one something, and I got, you guys gave me the probably that one, you got one. But it says at least one. So it can't just be the one, it could be multiple, all right? So make sure you're reading the question carefully. Some of you guys also got partial credit because you wrote out the notation correctly and then put the wrong numbers there. That'll do it every time. Other questions about at least. Is it making more sense what you should be thinking about when you think of at least? I want to make sure we get this cleared up before we move on to chapter 15. Jacob's good. What about everyone else?
How much time do you give?
I don't know yet. I've got my list. Remember I said I have my post-it note. Other questions on that part? All right. Someone in here describe to me, this is the other problem we have. Describe independent events. Just give me a scenario with independent events. Okay, rolling a fair die twice, right? And why are those independent? The first roll doesn't affect the second roll, right? Yes. We talked about in first period about the blood type question from the homework the other night, right? When you have 3 random people walk into the blood bank to donate blood, one's blood type does not influence the next person's. And then, of course, we had to talk about the vote twins because they wouldn't be independent, right? If you're talking about random people, those are independent. If you're talking about people that are related, blood type is not independent, right? One's going to influence the other. So you guys know independent. You guys can answer that part. But I'm making sure we really know independent because disjoint became the problem. Okay? So for disjoint events, and generally for disjoint events, you're about like one outcome, right? You can't be 2 different things at the same time. All right? So for example, if you flip a coin, yes, a coin has a head side and a tail side. But the outcome, it cannot land on both heads and tails at the same time, right? You can't land on both sides. It can't do that. Okay? You can only land on one side at a time. So disjoint events, you're talking about one outcome. It can't be both. It can be one or the other. Right. So throwing a die, you cannot get a 1 and a 6 at the same time. So the events of getting a 1 and getting a 6 are disjoint.
So it's not like
No, it's not the outcomes. Yes. Now, disjoint is not the same thing as independent. They seem like similar ideas, yeah? But if you have disjoint events, if you, for the heads and tails example, if you are just doing one trial of flipping a coin, you flip the coin, you get heads, right? Remember at the beginning of the book of that chapter we did that cumulative probability for the stoplight? Well, if you just flip the coin one time and you get heads, then the probability of heads was 100% because it happened 100% of the time. The probability of tails was 0. So that one outcome, it influenced the outcome of the other event, right? So those are not independent. So disjoint events cannot be independent. So if you flip a coin, you get heads, then that one trial so far, heads has happened 100% of the time. Well, if heads has happened 100% of the time, tails has happened 0% of the time, right? So in doing that, one outcome has influenced the other outcome. And that goes against what independence says. Independence says that one outcome does not influence the other. So disjoint cannot be independent. Disjoint, you're generally talking about one particular item, person. Independent, more often you're talking about multiple trials, multiple people, multiple things. Okay? Is everyone good with that? Okay, that's my rundown of chapter 14 things that we were still having trouble with. So we're good with those? Lingering questions? Again, everything else you guys did fine on. All right then. We're going to start chapter 15 today then. It is not going to be, we have a whole entire week to do chapter 15 and take the quiz because we're going to take it little step by little step, and then at the end we'll put everything together. So in chapter 15 we're still doing probability rules, but we're going to have some more complex scenarios that, you know how in chapter 14 it said make a picture all the time? And we said why would we make a picture of these M&M questions? We get it. In chapter 15 you're going to have to make a picture. It'll help you make more sense of the questions. I'm glad you like drawing. You're going to be drawing a lot. So today we're just going to talk about one rule and one type of picture. And that will be your homework. And then, like I said, after we go over this, I'm going to go over your project. Okay? All right. Chapter 15 starts on page 342. And as usual, I cannot just teach you things because I have to use the example that they're using in the textbook, because if not, you don't understand what they're talking about. You know how our book does things. So the example we're using in this chapter is we're talking about bills, like monetary bills. Okay? So it starts off, I'm trying to give you the short version. It starts off by saying, if you pull a bill from your wallet or pocket without looking at it, an outcome of this trial is the bill you select. Yes? So this sample space is all the bills in circulation. And so there's a $1 bill and a $2 bill and a 5 and a 10 and a 20 and a 50 and a 100. So those are the possible bills you might have in your wallet right now. If I took the bills out of my wallet, I would know what the outcome is because I know I only have $1. But maybe some of you guys are richer than I am. So if you pulled a bill out of your... See, there you go. But if you pull a bill out at random, those are technically what could come out of there. I don't know if any of you guys are high rollers carrying out hundreds, but you know. Excellent, Jacob. Excellent. So it's starting to talk about more stuff with the bills. We all know the monetary value, but then it starts talking about like pictures on the bills. So there are images of famous buildings in the center of the backs of all but 2 bills in circulation. The $1 bill has the word 1 in the center, and the $2 bill shows the signing of the Declaration of Independence. But every other bill, 5 and above, has a building. Okay? So then it says, what's the probability of randomly selecting a bill with an odd number value or a bill with a building on the reverse? Well, it just told me that besides the $1 and $2 bill, everything else has a building, right? It's like a $5 bill has a building on the back, right? So are these going to be this event A, a bill with an odd number, and event B, a bill with a building on the reverse? Are those disjoint events? No, they're not disjoint because the bill could have both, right? So if it's disjoint events, there wouldn't be any overlap, but now we have overlap. Just like, you know how in chapter 14 they ask you this question about like you're looking for houses, like realtor something, and you're looking for like houses with garages and houses with pools, and it said, why can't you just add the probabilities together? Because they weren't disjoint, right? The house can have a pool and a garage. Well, same thing here. A bill could have an odd number value and a building. All right, so now we can't just simply add the probabilities together. That would be nice, but we can't do it because there's overlap. So we've got these really pretty Venn diagrams. So the top one has the probability of A and B and the intersection. And the second one has this exact question about the monetary values and buildings and such. Notice the $2 bill is out here. What does that mean? It's not odd. And it doesn't have a building, right? It's still part of the sample space, though. It's just not in one of our categories. It's not an outlier. You know better than that now. All right, so we have this intersection, this $5 bill. So, plays a crucial role because it has both odd and has a building on the reverse. It's in both A and B, which places it in the intersection. And so the reason we can't simply add the probabilities of the A and B is that we count the $5 bill twice. And you can't do that, right? We've talked about that in chapter 14. So here comes the general addition rule. So we said the addition rule in chapter 14, you can just add 2 probabilities that were disjoint. Well, now if you have events that have an intersection, you can add the events and subtract their intersection. Okay, this is on the chapter 4 or on the AP Stats formula sheet, and you will have it to use from here out. So on a test, on a quiz, I will give you said rule. Okay. Now, could you have used this rule in chapter 14? Yes, you didn't need it, but could you have used it? Yeah, because what would the intersection have been? In 14, did you have any intersections? No, so it would have been 0, right? But you could have used it. So I'm just saying, on the AP exam, it's going to be nice to have this, right? Because you know you can use it for chapter 14 and 15 things, right? It works. If you add the 2 events together, you can subtract off the intersection, you should be okay. Anyway. So we're going to do one type of question today. And we're going to do questions in which you can use the general addition rule and use Venn diagrams to answer the questions. That's all we're doing today. We're doing Venn diagrams and then using the general addition rule. Can we handle it? All right. So here's the question I'm going to do with you guys, and then I'll give you the homework. So it says back in chapter 1, we suggested that you sample some pages of this book at random to see whether they held a graph or other data display. We actually did just that. We drew a representative sample and found the following. 48% of the pages had some kind of data display, 27% of the pages had an equation, and 7% of the pages had both a data display and an equation. All right? Now, I'm going to add in a question before we do the other ones. I'm going to ask this question. What's the probability of getting a page with a data display or a page with an equation? How am I going to figure this OR question out? We have to use the general addition rule, right? We have to add the two probabilities together. So the probability of a page with a data display plus the probability of a page with an equation. But there are some pages that have data displays and equations. So I subtract the intersection, right? I'm just going to say intersection. We all know what that means. So I'm going to have 0.48 plus 0.27 minus 0.07. And that ends up being 0.68 or 68%. Everyone go with that? So that is one way you would use the general addition rule. You use it for OR questions. Okay? Yeah. Now, the other questions we have to answer are not so straightforward, which is why we're going to draw a Venn diagram, because we're going to make our lives easier. Okay? Can I erase what's on the screen right now? All right, so I'm making mine all pretty. Perfect. Now, what percentage is in the intersection that has data displays and equations? 7%. So we're going to put a 0.07 in the middle, right? Yeah. Now, for the data displays, it says 48% have data displays, but that is including the 7% that have both. So we have to subtract off the intersection all the time to make sure we get the right amount in each of the circles. So this will be 0.41. And then for the equation pages, that's 27 minus 7, so 0.2. But that does not add up to 100%. So we get what? .32. All right, so here's our Venn diagram. Now that we have our Venn diagram, I can answer these nice little questions. So in part B, what is the probability that a randomly selected sample page had neither a data display nor an equation? So which one of these numbers represents no data display and no equation? Would that have been harder to answer if you didn't have a picture? Probably. On C, what is the probability that a randomly selected sample page had a data display but no equation? 0.41. Do you see how the Venn diagram can be helpful to you? Yes? All right. Your homework then is just 4 questions just like this. They are on page, someone check me, but I think it's 341. 341. 341 is? Yeah. So page, what's the first page of the exercises? 361. There we go. Number 1 through 4. Oh, do it.